In this video, we introduce a variety of function transformations. So what we want to figure out is how does the change in a function's formula relate to geometric changes of the curve in the plane? So we're going to cover several cases of function transformations. First, we look at vertical translation, or a vertical shift of a function. So that's a change in the formula that slides the function up or down in the plane. Then we look at horizontal translation, in other words, a shift left or right in the plane. Next, we get into reflections of a function, starting with vertical reflection, in other words, a reflection about the x-axis, and then horizontal reflection, which is a reflection about the y-axis. Finally, we look at horizontal and vertical compressions and stretches of a curve. So we're going to make changes to a function's formula that squash the function vertically or stretch it out like this, and changes that squash the function horizontally or stretch it out like this. Now, since we're covering so many cases in this video, I've divided it into these three major chapters for easier navigation if you want to skip around. And we'll start things out with vertical translation of a function, in other words, an upward or downward shift in the plane. Now, what we're looking at is a graph of some original function that we're going to call f of x. And our choice of language and notation can be really helpful to our intuition here. We're going to say, compared to the graph of f of x, the graph of g of x, defined by f of x plus k, is shifted vertically by k units. So the modification to the formula we're talking about is that we simply take the formula of f of x and we add a number to it. So why should this cause a vertical shift? Let's just be more concrete about it and say that k is equal to 2. So we want to graph g of x where that's defined by f of x plus 2. And if we start looking at individual points on the graph, so I'm just going to start with the origin here. It looks like f of x passes through the origin. Then I can find g of 0 by taking f of 0 and adding 2 to it. Well, f of 0 appears to be 0, so I end up with 2 for g of 0, and we've got the first point on the graph. Now, as we continue to look at more x values, there's nothing surprising here. Every time we plug in an x value, we get the f of x corresponding to that value, and then we add 2 to it. In other words, every y value on the graph of g of x is simply 2 units higher than the y values on the graph of f of x. So it's also possible that k is a negative number. So in our next example, let's graph g of x defined by f of x minus 3. And just to make things interesting, I'll choose a different x value to focus on. So we're looking at x equals negative 3, and it looks like f of x is a little less than a half right there. So when we evaluate g at that location at x equals negative 3, we get g of negative 3 is f of negative 3, just the y value on the original curve, minus 3. In other words, a y value that is 3 units lower in the plane. So just as an approximation, f of negative 3 was about a half, and so we're going to go 1, 2, 3 steps below that, and we get a g value of about negative 2.5, 3 units lower than the original f value. And of course, as we look at more values of x, every y value on the graph of g of x is just going to be 3 units lower than the y value on the graph of f of x. So here's a quick example of a vertical translation problem. We're asked to use the graph of f of x equals absolute value of x. So this v-shaped curve is the function absolute value of x. And I'll post a link to the video where that was first derived. And then our goal here is to sketch the graph of g of x given by absolute value of x plus 2. So all we have to do is take every y value on this graph and shift it up by 2 points. So after the translation, we get this same v-shaped curve, but it's been shifted up by 2 units. And there's the graph of absolute value of x plus 2. Next, we're going to look at horizontal translations. So this time, we're told that compared to the graph of f of x, the graph of g of x defined by f of x minus k is shifted horizontally by k units. So the concept here is that we replace the x with x minus k in the formula for f of x. Now we need to clarify one point here. If k is a positive number, we're going to see a rightward shift, and if k is a negative number, we're going to see a leftward shift. So again, to get a grip on this, we're going to think concretely about a specific case. Let's graph g of x given by f of x minus 1. And I'm just going to start by thinking about the x value 1 and figuring out what should g of 1 look like. So we just sub in 1 for the x, and g of 1 turns out to be f of 1 minus 1. Well, 1 minus 1 is 0, so g of 1 is f of 0. In other words, we took the vertical value from 1 unit to the left and shifted it over to the right. So g of 1 is going to have that same value that f did, 1 space to the left of it. And of course, we can continue this for as many x values as we like. I'm just going to pick one more. I'm just going to look at x equals 2. And g of 2, that's going to be f of 1. In other words, the y value on this new curve g is the same as the y value on f of x, just 1 space to the left. F of 1 looks like about 2/3 or 3/4. It's about this high. And we get a second point on the graph of g of x. So every time we pick an x value, the corresponding y value is going to be the y value for f of x, but taken from 1 space to the left. So this is a rightward shift by 1 unit. So now we look at an example where k is negative. So I'm evaluating f of x plus 2. Now, given the way we wrote this, that means k is negative 2. So we're expecting a leftward shift by 2 units, and let's just look at 1 or 2 points to figure out why. And I'll just go ahead and look at x equals 0. I want to evaluate g of 0, so I'll plug in x equals 0, and it turns out g of 0 is the same thing as f of 2. In other words, we take this vertical value on the graph of f of x, sitting here at x equals 2, and we move it over 2 spaces to the left, and we have our first point on the graph of g of x. And it's going to continue this way for every value of x we choose. We're going to grab the y value from the graph of f and move it over 2 spaces to the left. And this results in a horizontal translation to the left by 2 units. So this time in our example, we're turning things around. This time we're told that the yellow curve is the simplest parabola. F of x is x squared. And we're given a second graph that appears to be a leftward translation of that simplest parabola. That's g of x, and we want a formula for it. So what I notice is the vertex is clearly bounced 3 spaces to the left. If you follow every other point on the graph, you'll see that it's been moved 3 spaces to the left. So this is a leftward translation by 3 units. That means k is negative 3, and that means g of x is f of x plus 3. Now all we have to do is sub in x plus 3 for x in the formula for f of x, and we arrive at a formula for g. It's x plus 3 quantity squared. Just as a really quick check on our work, we can verify that this is working for the vertex. So I can look at g of negative 3, and that is 0, just like the graph, and we're done. So next we're going to look at vertical reflections. And we're told that compared to the graph of f of x, the graph of g of x defined by negative f of x is reflected vertically across the x-axis. So all we're doing here is taking the formula for f of x and putting a minus sign in front, or you can think of it as multiplication by negative 1. So if we start to investigate point by point, I can look at, for example, x equals 1. And f of x looks like about 2/3 or 3/4 there. And I can think about the approximate value of g. So I have g of 1. Well, that's the negative of f of 1. So I end up with about negative 2/3 or negative 3/4. That's going to appear right here on the graph. So that y value on the graph of f of x was reflected to its negative below the x-axis by the same distance. Now this works for negative y values as well. We can look at x equals negative 1 as an example. At x equals negative 1, f of x looks like about negative 0.4. So g of negative 1 is going to be the negative of f of negative 1. Well, if f of negative 1 is about negative 0.4, then the negative of that is about positive 0.4. So that point has been taken to its reflection across the x-axis, the same distance from the x-axis, but on the opposite side. So when we apply this process to all the values of x, every one of those y values being taken to its negative on the opposite side of the x-axis, we end up with a vertical reflection of the entire function. So in our vertical reflection example, we're told that f of x is the sine function. And we're already given a graph of the sine function, and then we're asked to use that to graph g of x equals negative sine x. So we simply take every point on this graph and reflect it across the x-axis, and we arrive at the graph of negative sine x. Like if I look right here at x equals negative pi over 2, the sine of negative pi over 2 is negative 1. Well, the negative of that is positive 1. So if we go along the graph and just reflect every single point, we've got the graph of g of x equals negative sine x. Next, we talk about horizontal reflections. So we're told, compared to the graph of f of x, the graph of g of x equals f of negative x is reflected horizontally across the y-axis. When I say f of negative x, I mean if I take the formula of f and I replace the x with a negative x, that's what causes this kind of horizontal reflection. So to figure out why this is working, we can just look at one or 2 points on the graph. I'll go ahead and look at x equals 1. And g of 1 is going to be the same thing as f of negative 1. So I have to look for the y value over here on the opposite side of the y-axis. And here's my f of negative 1. That y value, something like negative 0.4, ends up on the graph of g. If we sub in x equals 2, g of 2 is f of negative 2. So we take the y value from over here and we translate that over here for the graph of g. We can also go the other way around and look at negative values of x. So like g of negative 3, for example, that's going to be f of negative 3, or f of 3. So when I want to find the g value over here, I look for the f value on the opposite side of the y-axis, the same distance from the y-axis, and that's right there. So that y value gets translated over here. Now taking every single point on the graph of g and moving it the same distance on the opposite side of the y-axis, that's just a horizontal reflection of the graph like this. In our example, we're told that we're looking at the graph of f of x equals e to the x. This is the natural exponential curve. And we want to use that to graph e to the negative x. So we notice the relationship between these two formulas is that if I take the formula for f of x and I replace x with negative x, that gives me the formula for g. In other words, g of x is f of negative x. And that's precisely what causes a horizontal reflection. So there's the graph of e to the negative x, just a horizontal reflection of the graph of e to the x. So finally, we get into our stretches and compressions. So we're going to start with vertical stretches and compressions. And we're told that compared to the graph of f of x, the graph of g of x equals k times f of x. In other words, multiplying the entire formula for f of x by some constant is going to be stretched vertically by a factor of k. Now it's important to clarify what I mean by stretched, because we're actually talking about two different cases. If we multiply the graph of f by a number bigger than 1, it's going to be stretched vertically. But if that number has a magnitude less than 1, so a fraction like 1/3 or 1/2 or whatever you can imagine, that's going to cause a vertical compression of the graph. And we're not going to explicitly cover the case where k is less than 0, because that's actually a combination of two function transformations. If k is less than 0, you have a stretch compression transformation combined with a vertical reflection because of the minus sign. So to get a sense for why this works, we'll start by talking about points on the graph of g of x equals 2 f of x. And I can just go point by point as usual. Let's focus on x equals 1. Here's the f value there. It's something like 2/3 or 3/4, somewhere in that neighborhood. And g of 1 is going to be twice that. It's 2 times f of 1. So we just double the y value and we end up here somewhere in the neighborhood of 1.5. If we continue that at x equals 2, I have a number slightly bigger than 1 for the y value on the graph of f of x, and that gets doubled, and we end up here. So we're simply doubling all the y values. Notice that when y is negative, we do the same thing. If I look at x equals -1, g of -1, it's going to be twice f of -1. And since f of -1 is negative, I'm just doubling that negative number, and I end up twice as far away from the x-axis. So doubling every single y value, we end up with our final graph for g of x. So now let's look at a k whose magnitude is less than 1. So this time we're multiplying f of x by 1/2. And I'll start with x equals 1 again. And g of 1 is going to be 1/2 f of 1. In other words, 1/2 the original y value. So I just take this original y value and cut it in half. And it looks like it's about right there. And I can continue this with x equals 2, cut the y value in half, x equals 3, cut the y value in half. And of course it works for negative numbers too. For x equals -1, I get something like that. X equals -2, something like that. Okay, so we just continue this for all the x values in the domain of the function, and the result is to flatten the graph by a factor of 2. In our example, we're given the graph of the cosine function. So f of x is equal to cosine x. And first we want to graph 2 cosine x. So we can focus on a couple specific points. At x equals 0, cosine of 0 is 1. And that means g of 0 is going to be 2. So that's just twice the original y value. Notice what happens at the minima of the cosine function. Its minimum value is -1, and that gets transformed to -2. And I can do that for this other minimum as well. And the net result is that we've just doubled the amplitude of this cosine function. It now oscillates between 2 and -2 instead of 1 and -1. In the second example, we want to plot 1/3 cosine x. Well, every y value of the cosine function is simply multiplied by 1/3. So now its amplitude is 1/3. It's oscillating between -1/3 at the bottom and 1/3 at the top. So the whole thing has been flattened closer to the x-axis by a factor of 3. So finally, we're looking at horizontal stretches and compressions. And this happens when we multiply the argument of f of x by a constant. So when we replace x with kx, it causes a horizontal stretch or compression. Now the rule for this is kind of reversed. If the magnitude of k is bigger than 1, that's going to cause a horizontal compression of the graph. And if the magnitude of k is less than 1, that's what causes a stretch. And again, we're not going to explicitly treat the case where k is less than 0 here, because that minus sign means we would have a combination between a stretch or compression and a horizontal reflection. So we'll start by thinking about what the graph of f of x over 3 should look like. Notice that that's totally equivalent to f of 1/3 x. In other words, k is 1/3 here. We're supposed to get a stretch. So just to keep the numbers nice, if I look at g of 3, so we're investigating this x value right here, that's going to be f of 3 over 3, which is f of 1. So the vertical value for g at x equals 3 is the same as the vertical value for f at x equals 1. So we just take this vertical value and shift it over here. Okay, so there's g of 3. Notice that the same thing is going to happen if I look at g of -3. That gives me f of -1. So if I'm trying to find my g value here, I have to look at my f value all the way over here at x equals -1. So something like this. Now to really get a sense for what's happening, we actually would need a graph that was slightly bigger, but we can at least imagine what's going to happen here. G of 6, that goes one space off the graph, would be f of 2. So I'm taking the f value from here and then plotting it all the way over here. So every point on the graph of g is simply 3 times as far away from the y-axis as the points on the graph of f of x. So let's look what happens if we have a k with a magnitude bigger than 1. Again, we're just going to make it a factor of 3. So I have f of 3x. In other words, x has been replaced with 3x in the formula for f. If I look at x equals 1 here, I'll get a g of 1 that's equal to f of 3. So the y value on g is taken from the f value 3 times as far away from the y-axis. So I'm going to use this f value, and that ends up on the graph of g. Notice that the origin is also on the graph of g because g of 0 is the same thing as f of 0. Okay, again, it requires us to use our imagination and go off the graph, but g of 2 would be the same thing as f of 6. So I would need the y value at x equals 6, somewhere up here, I think, and that ends up being the y value for our new function g at x equals 2. So every single point on the graph of g of x is brought closer to the y-axis by a factor of 3. And notice in the animation, this is revealing some parts of the original function f of x that we couldn't see in the original picture. Okay, so to wrap things up, we'll look at an example of a horizontal stretch and compression. And for this, we're using the function x cubed minus x. So this is a simple cubic function with roots at x equals -1, 0, and +1. We want to use the graph to sketch the graph of g of x, where g of x is given by this, x over 2 quantity cubed minus x over 2. Well, all that is a replacement of x in the original function. G of x was obtained from f of x by replacing x with x over 2. Now we already know that's a horizontal stretch by a factor of 2, so there's the graph of g of x. In particular, we can pay attention to the roots of the function. F of x had a root at -1, g of x has a root at -2. And the other root was +1 on f of x, and that's going to be +2 on g of x. Now in the second question, we just have a horizontal compression by a factor of 2. This formula for g is obtained from f of x by replacing x with 2x. So there's the graph of our horizontally compressed function. And again, I can just track the roots to make sure things are working. Instead of a root of -1, I now see -1/2. And instead of 1, I now see +1/2. In other words, every point on the function is brought closer to the y-axis by a factor of 2. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.